Hey everyone. All right, so we're going to get started by graphing the trigonometric parent functions. So to start off, I would definitely recommend filling out the unit circle at least one time. The more the merrier, of course, but at least stop here, fill it out, and then let's get started after. All right, so some really important vocab that we're going to talk about first is just domain and range, which hopefully this is not new. So domain and range, of course, we talked about all the way back from middle school. So your domain is going to be the spread of how far something left and right your graph is going to go. And then your range is going to talk about how far up and down your graph is going to go. So some more mathematically correct notation or verbiage on how you would say this is all the elements of your x value for your domain or all the elements of your y value for your range. So elements just refers to all the values that are going to be part of that function or part of that graph. So it's just a little bit more mathematically correct, but tomato, tomato. So the next thing we're going to talk about is what we call the cycle. So a cycle of a graph is just going to be one section of a graph before it repeats. Now, the types of graphs that we're going to be looking at are going to do what we call oscillate. So when I say oscillate, it's going to kind of do this wavy-like function, or pattern rather, and it's going to do it a repeated number of times. So when I say a cycle, we're looking to see how many times that same pattern happens. So if I start over here, I notice how it's going to start in the middle and then go up, and then kind of curve back down and then back up. But then I also notice, oh, well, it's going to start again. Start in the middle, go up, curve back down, back up, and then I'm going to have another part right here. So each of these individual parts right here are what we call cycles. So as you can see, we're going to have multiple cycles within a graph. Okay, and then the next part that we're going to look at is what we call the period. So the period is going to be the number of degrees or radians in a single cycle, meaning we're just going to measure how long each cycle is. So the length of that cycle is what we call the period. Now, each cycle should be the same in your graphs. Okay, so for the next part, now we're actually going to look to see what's the default period for your trig functions. So we're going to start with just your sine and cosine functions, and then by default, that's also going to refer to your cosecant and secant functions, since those are reciprocal functions of sine and cosine. So the periods of sine and cosine will also dictate the period of cosecant and secant, respectively. So in order to determine that period, we're actually going to go back up here to the unit circle. So what I want to do is let's look at the sine values. So we're going to start with the y values. So if I look at the y values, we're going to go from 0 to 1/2 to root 2 over 2 to root 3 over 2 to 1, so on and so on. But notice we only have to go halfway around to go from 0 to 0. So there's a first repeating value. However, the issue is we've only accounted for all the positive values. We also need to account for all the negative values. So in order to account for each and every single value on the unit circle for sine and cosine, we have to go one full rotation, which is the equivalent of saying 2 pi radians. So your period for sine, cosine, cosecant, and secant will be 2 pi. Now for tangent and cotangent, now to look at the period for this value, remember, we want to go through both the positive and the negative values for each of these trig ratios in order to consider it a full period and a full cycle. So to go from our tangent values, so we're going to start at 0, and then we're going to go all the way around until we get to our repeated value, but where we account for both the positive and the negatives. So in quadrant 1 over here, we went through all the positive values. Quadrant 2, we went through all the negative values. And then we went to repeating values, which means we only had to go halfway around the unit circle, which means your period for tangent and cotangent will be just 1 pi. All right, and then looking at the next part, so your asymptote is going to be a dashed line or curve that's going to indicate where a function is undefined. Now, for the sake of what we're doing, we're just going to be using dashed lines. We're not going to have any curves, thankfully. We saved all the curved asymptotes for polynomials when we had parabolic asymptotes or even cubic asymptotes, but we're not going to have any of those, thankfully. And then zeros, as just a recap, It's just a fancy way of saying your x-intercepts, which are also known as solutions, roots, or just your zeros. So we could use any sort of those values or names for your x-intercepts. All right, so to get started, what we're going to do is now we're going to actually graph your sine function. So we're going to first fill out a table based on the unit circle. Then based on the table, we're going to fill out the graph. And then based on the graph, then we're going to fill out the attributes. Okay, so to start off, your x value is going to represent the radian. Now this is from the unit circle. And then your y value is going to represent sine of that radian. Okay, now we chose these specific radian values on purpose. We counted by pi over 4. So we went to 0, pi over 4, pi over 2, 3 pi over 4, pi. So just to kind of give you an idea, we did 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and then all the way back to 2 pi. So we did all the way around, but we chose just every fourth. Okay, so starting off, now we're going to look at filling out these values. So if I do sine of 0, well, you get 0. If I do sine of pi over 4, well, that's going to give us root 2 over 2. Now, root 2 over 2 is about 0.7. So that'll come in handy for when we're actually graphing. All right, and then sine of pi over 2 is going to give you just 1. Sine of 3 pi over 4 is going to give you positive root 2 over 2. Sine of pi, which is going to give you 0. Sine of 5 pi over 4, which is going to give you negative root 2 over 2, which once again is going to be about negative 0.7. And then 3 pi over 2, which is going to be negative 1. 7 pi over 4, so we want sine of that, negative root 2 over 2. And then sine of 2 pi, which is going to give you 0. Okay, so now what we're going to do, if you look at your little graph over here, we actually already have the radians already labeled on the graph for you, but just know that they're not always going to be given to you, so you may have to come up with your own scale. So that'll also come up in a later lesson. So now we're going to fill out this graph. So each of these are going to represent coordinates. So I'm going to have the coordinate 0, 0, pi over 4, comma, root 2 over 2, pi over 2, comma, 1, 3 pi over 4, comma, root 2 over 2, so on and so on. So I'm going to have a point at 0, 0, and then at pi over 4, I'm going to have about 0.7. So I'm going to approximate, it's going to be about right here. And then pi over 2 is going to be at 1. And then we're going to go back down to 0.7 at 3 pi over 4. And then at pi, we're going to come down to 0. And then at 5 pi over 4, it's going to be negative 0.7. 3 pi over 2 is going to be negative 1. And then 7 pi over 4, we're going to come back to negative 0.7. And then 2 pi, we're going to come all the way back to 0. So if you look at this pattern, if I were to connect all these points, it's going to give you this curve pattern, just like this. Let's see how well I can draw. Fingers crossed. Perfect. Kind of. We'll take it. All right, so a couple notes about when you're drawing. So notice how these are pretty smooth in terms of curves. If you were to draw these kind of linear and then give them corners like this and make it kind of jagged, we would count that wrong. It has to be a very smooth curve as it goes throughout your graph. So just keep that in mind when you're drawing. So it has to be a smooth curve once again. Okay, so now that we have our graph, now I'm going to come over here and we're going to do our attributes. So the domain of your function, so while we only drew one cycle, your function technically is going to keep going indefinitely in both directions. So if I were to just say the domain of the entire function, well, I would say it would go from negative infinity to positive infinity. Now, if I were to say of just the first cycle, well, the first cycle, that would go from 0 to 2 pi. So just keep in mind on what we're really asking for. If I just asked for the domain, then you would assume it would be the full thing. But if I am specifically asking for just the first cycle, then you need to make sure that you're using the brackets since it can be a closed interval. All right, now for the range, we're looking to see how far up and down this function goes. So I can go as low as -1, and I can go as high as +1. So your range, we're going to go in between -1 and +1. Okay, and then for the number of cycles, well, we only graphed one cycle. And then the period is, well, by default, it's just 2 pi. So if you look, we went from 0 and we stopped over here at 2 pi, so the length of this cycle would be 2 pi. Okay, and then over here, the next part is what we refer to as the frequency. Now the frequency, in order to find this value, this is just going to be 1 over the period. And then you're going to simplify that value. So 1 over the period, in this case, would just be 1 over 2 pi. So that would be your frequency. All right, and then in terms of asymptotes, now we are not undefined on any of these values. So for asymptotes, you can just write none. Okay, and then for your zeros, we want to account for all the zeros. So this is where that math notation up here at the top is going to come in. So because we want to account for all the zeros, we want to account for all the times that it hits the x-axis. So we want at 0, we want at pi, and we want at 2 pi. So what this means that we're going to do is we want to account for just all the pi values and all the multiples of pi. So I'm going to want the x values are going to be all the multiples of pi times some value. Now that k value here, we have to define that value. Because if I just write pi k, well, I don't know what k is. So you have to define what that k value is. So I'm going to say k is an element of the integers, which is a number group. So we have the variable, and then the epsilon here is the symbol or fancy notation of saying is an element. So that's why we also talked about the element up here. So we're saying k is an element of the integers. So that's what this information up here is telling you. So we have to always define what your variable is whenever we have multiple values. Okay, so there is your sine value. So now we're going to come back and we're going to do cosine. So for cosine, once again, we're going to start with the table. So cosine of 0 is going to be 1. So let me backtrack a second. So your x values are going to be your radians. And then your y value, this is going to be cosine of that radian. So remember, now we're going to be shifting gears and we're looking at the x values. So sine, we were looking at the y values. Cosine, we're looking at the x values. So if I go back up to my unit circle, now we're going to start with 1, then go to root 2 over 2, then 0, negative root 2 over 2, -1, so on and so on. Okay, so at pi over 4, now we've got root 2 over 2. And then at pi over 2, we've got 0. At 3 pi over 4, we're going to have negative root 2 over 2. At pi, we got -1. 5 pi over 4, we're going to have negative root 2 over 2. 3 pi over 2, we're going to have 0. 7 pi over 4, we're going to have positive root 2 over 2. And then at 2 pi, we're going to have 1. Okay, so now when I graph all these values, so quick recap, root 2 over 2 is going to be about 0.7. So when I plot these points, so at 0, 1, then 0.7, 0, negative 0.7, -1, and hopefully you can kind of see a pattern as to what your graph is going to look like. So it's almost like a V shape. So I know a lot of people look at this and they're going to think, oh, like an absolute value. Well, when you look at the points like this, kind of, but remember, it has to be a smooth curve. So you need to make sure that you curve your graph. Because remember, this is going to oscillate. Okay, so I'm going to attempt. Close enough. I missed, but it's fine. Ooh, excuse me. All right, so now we're going to look at the domain, the range, number of cycles, period, so on and so on. So for your domain, in just this, or rather, the full domain, because it's going to keep going indefinitely, remember, it's going to oscillate back and forth indefinitely in both directions. So if I'm talking about the full function, it's going to be negative infinity to positive infinity. But if I'm talking about just the first cycle, then my first cycle would just be from 0 to 2 pi. So just be careful. Remember, make sure you're paying attention if I want the whole thing or if I just want the first cycle. So the range, once again, so it's going to go all the way down to -1, but it's going to come all the way up in two places, all the way up to +1 on both of those. So your range, so from -1 to +1, number of cycles, well, we only did one cycle, and that's going to have a period of 2 pi, with a frequency of 1 over the period, which is 1 over 2 pi. And then we don't have any asymptotes. We don't have any discontinuities or any values that are undefined. Ooh, excuse me. All right, and then your zeros, what we're going to look for is when it crosses the x-axis. So we have it at pi over 2 and 3 pi over 2. So whenever we have the pi over 2s, so that means your asymptotes, we're going to start, and we're going to do x equals pi over 2 plus pi k, where k is an element of the integers. Or if you want to say kes, you can say kes. Remember, they're not going to know, or we as your graders are not going to know what you say, just what you write. So you can write kes, just don't tell us kes. All right, so now we're going to move on to tangent. All right, so tangent, if you look back at the unit circle, those are going to be your values in orange. Okay, so for your values in orange, ooh, sorry, y'all. So when I plot all these values, so we're going to have 0, 0, pi over 4, 1. Sorry, y'all. All right, and then pi over 2 is going to be completely undefined. 3 pi over 4 is going to be at -1. Pi is going to be at 0. 5 pi over 4 is 1. At 3 pi over 2, we are undefined. And then 7 pi over 4 is -1. And then 2 pi, we're back at 0. Okay, so anytime we're undefined, what this means, sorry, y'all. So what that means is we're going to have a vertical asymptote. So I'm actually going to go ahead and draw these vertical asymptotes. So on my iPad, what I'm going to do, I'm going to shift over here, and I'm going to go to a dashed line at pi over 2, vertical dashed line, and then at 3 pi over 2, another vertical dashed line. Come on, there we go. All right, so now I'm going to start plotting these points, and we're going to look to see what kind of pattern we're going to have. So we're going to have a point at 0, 0, then pi over 4, 1. All right, pi over 2 is undefined, so we're going to skip over it. 3 pi over 4 is -1. Then pi is at 0. Then 5 pi over 4 is going to be at 1. And then 3 pi over 2 is undefined. And then 7 pi over 4 is -1. 2 pi is at 0. So that's all we have for right now. But I'm actually going to expand on this in a bit. Oof, sorry, y'all. All right, so for tangent, what your graph is going to look like, I'm just going to focus on just this middle section right here. So with these 3 points, what's going to happen, I'm actually going to be starting at the bottom left over here in this section and then ending in the top right over here. So what's going to happen, your graph is going to pass through these points and then kind of get more and more vertical as we get closer and closer to those asymptotes. So over here, even though it's technically incomplete, when we get to 2 pi, I'm going to have another point over here. And then we would have another little cycle over here. And then we'd have another vertical asymptote. Ooh, that is not dashed. We would have another vertical asymptote over here. And then same idea over on the other side. So we're going to have at negative pi over 4, that would be at negative 1. And then we would have another cycle going over here. And then once again, we would have another not horizontal. We would have another vertical asymptote over there. So we're going to have repeats of what this function looks like on multiple periods or multiple cycles. Okay, so for your domain, my bad. So for your domain, what we're doing is we're just going to be looking to see when it's not defined. So we essentially need to write the equations of all the asymptotes. Okay, so for your domain here, what you're going to do is you're going to say it's all the x values where we're not equal to those asymptotes, which would be pi over 2 plus pi k, where k is an element of the integers. Wow, that's actually terrible. Close enough. All right. Now notice, I know this is a very small but very important detail. Notice right here how we did not equal to. So that excludes, oops, sorry, y'all. This is why you don't record when you're kind of sick. So we are not including these vertical asymptotes. So that's what we're doing up there. We're saying x can be anything except for those values. Now for the range, I'm going to come back over here. We're going to go down indefinitely and then up indefinitely, which means your range is going to be all real numbers. So from negative infinity to positive infinity. All right, and then your number of cycles. So let me actually kind of go back to our default. So by default, we didn't have that part, and then we didn't have this part. So we only had this one full cycle right here, and then we have this half cycle here, and then, whoops, hold on. All of that should be crossed out. There we go. So we have the full cycle here in the middle, then we have a half cycle over here and another half cycle over here. So if you think about it, 1/2 plus 1 plus another half. What do we get? We get 2 full cycles. All right, and then with your period and tangent, that's going to give you just 1 pi. Then your frequency is going to be 1 over the period, which means your frequency, we're looking at 1 over pi. And then your asymptotes, so what's really handy about this is you're actually just going to copy and paste what you did for the domain down here for the asymptotes. The only difference is now it's going to equal pi over 2 plus pi k, where k is an element of the integers. So up here for the domain, we're saying what it can't be equal. Now all the asymptotes are pretty much saying those are the values that we are excluding. Okay, now for the zeros, so now we're looking to see where are we going to touch the x-axis. So I'm going to get rid of all this that I crossed out. So I specifically am going to emphasize that we want at 0, at pi, and at 2 pi. So whenever that happens, that means we just want the pi k's. So that means your zeros are going to be x equals pi k, where k is an element of the integers. Okay. All right, now moving on to the next section. So I will say these are going to be your big 3 that you've got to know. So for cosecant, secant, and cotangent, these are going to kind of follow from these 3. Okay, so now kind of getting into cosecant. So once again, we're actually going to start with the table. Actually, scratch that. No, we're not. So with cosecant, what you need to remember is that cosecant is the same as 1 over sine. I don't know why I stopped there. So what I'm actually going to do, in order to make graphing these functions a little bit easier, I'm actually going to start with sine. So I'm going to attempt to graph let's see how this goes. Not bad. Okay, so more specifically, what I'm going to do is I'm going to make this dash, and I want to make it kind of thin. I don't want to bring a lot of attention to it. I just want to use it as kind of a foundation. Okay, so what's going to happen is we're doing 1 over your sine value. Okay, so let's actually fill out that table so you can kind of get an idea. So if I do sine of 0, that gives me 0. So if I do 1 over 0, well, that's undefined. So right off the bat, we already have an undefined value. So sine of pi over 4, sorry, y'all, bear with me. So sine of pi over 4 is going to give me root 2 over 2. If I do 1 over root 2 over 2, that's going to simplify and give me root 2. Okay, and then sine of pi over 2 is 1. Flip it. We're going to do 1. All right, sine at... Yes, sorry. So sine at 3 pi over 4 is going to be root 2 over 2. Flip it, and then simplify, and you're going to get root 2. And then at pi, you have 0. So if I flip it, I get something that's undefined because I can't divide by 0. 5 pi over 4 is going to give you negative root 2. Then you're going to get negative 1, negative root 2, and then last but not least, undefined when you continue that pattern. Okay, so the reason that I'm doing this is because essentially every time your function sine is going to touch the x-axis, that's actually going to be every single place that we're going to have a vertical asymptote. So what I'm going to do here is I'm going to graph and do vertical asymptotes every time sine touches 0. Okay. And then the next thing that's going to happen is now you're actually going to draw your actual cosecant shapes. So your cosecant shape, I'm going to make this even smaller, and I'm going to make it gray. I want it to kind of fade in the background. So your cosecant shapes are actually going to be these kind of U shapes. So if I look at pi over 4, we're going to be root 2. So it's going to be a little bit bigger than 1. It's about 1.4. So that's about right here. Well, ish. I'm guessing, y'all. All right, and then at pi over 4, it's going to be at 1. So it's right here. And 3 pi over 4, it's going to be back at root 2. Okay, and then we're undefined. And then down here at 5 pi over 4, it's going to be negative 1.4, then negative 1, then back to negative 1.4. So we're going to have these little bowl shapes or U shapes or like lowercase n shapes. So what it's going to look like is something like this, and it's going to loosely follow. There we go. It's going to follow the direction of your asymptotes. So then down here, I'm going to start close to the asymptote, pass through these points. Well, try to. And then we're going to have these U shapes or these bowl shapes. So what you notice is every time it crosses, well, I say it, every time sine crosses through the x-axis, we're going to have an asymptote. And then every time it has a maximum or a minimum, that's where you're going to have your bowl shape. So once again, sine's going to oscillate all the way back and forth, which means cosecant is going to continuously have all these bowl shapes throughout the entire function. So we're just drawing one period, but just know that these little bowls are going to be going everywhere. Okay. All right. So now for your domain, we're going to see what we can exclude. So we're going to exclude at 0, pi, and 2 pi. So that's going to be the pi k's. So x is not equal to pi k, where k is an element of the integers. My handwriting is so bad. I'm so sorry. All right, and now for the range. So we are going down indefinitely, and then we're going up indefinitely. However, we are going to have this little gap right here. Notice how your function doesn't actually go in between here. So we are going to have a little gap. So what this tells me is we're going to go from negative infinity to negative 1, and then we're going to have union, pick it right back up at 1, and then go to infinity. Okay, now for the number of cycles in this graph, so in this case we only have 1, we're going to have a period of 2 pi since we're following the same logistics as sine, and then frequency would be 1 over that period. Then your asymptotes, so your asymptotes are going to start at 0, pi, and 2 pi, so we're going to just copy and paste what we have for the domain. So that's going to be x is equal to pi k, where k is an element of the integers. Okay, and then your zeros, we're looking to see where your little bowls, we're looking to see where these cross the x-axis. Well, they don't. So that means we're going to have none. Okay. All right, so same idea. Now we're going to move on to secant. So secant, let's do green. Who doesn't love green? All right, so secant is going to be 1 over cosine of x. That's actually terrible. That's still terrible. Close enough. So 1 over cosine of x. Okay, so we're going to start with the table once again. All right, so at 0, so we have our radian. And then we're going to have secant, yes. Secant of that value. So you're going to take the cosine of it and then take the reciprocal. So cosine of 0 is going to be 1. Take the reciprocal, well, it's 1. If I do cosine of pi over 4, that's root 2 over 2. Take the reciprocal, and we get root 2. Okay, now root 2 over 2, if I do cosine of root 2 over 2, that's going to give you 0. Take the reciprocal, and that's going to give you undefined. So what that tells you is we're going to have a vertical asymptote here. So anytime it's undefined, that tells you we're going to have a vertical asymptote. Okay, so now 3 pi over 4, that's going to give you a value of negative root 2 over 2, which is going to give you a reciprocal value of negative root 2. And then at pi, it's going to give you negative 1, so now I'm just going to kind of go through the values. Negative root 2, 3 pi over 2 is going to be undefined, which means we're going to have a vertical asymptote over here. Okay, and then at 7 pi over 4 is going to be positive root 2, and then positive 1. Okay, so those are the actual secant values, but I want to start by graphing. Wait, where are you going? Come back. Go back over there. Okay, so I'm going to start by graphing cosine. So with cosine, we're going to start at 1, then 0.7-ish, 0, negative 0.7, negative 1, negative 0.7, 0, positive 0.7, then back up to 1. Don't get sick, y'all. 0 out of 10 recommend. All right, so there's cosine. So I'm going to kind of put it in the background. So similar idea to cosecant, we kind of did all the hard work up here. Anytime it touches the original function, this little function here. So anytime your sine or cosine function touches the x-axis, that's how you know you're going to have a vertical asymptote. And then when you have a minimum or a maximum, that's where you're going to have one of your bowls. Okay, so Now what we're going to do, I'm going to come up here. I'm going to go ahead and draw all the asymptotes first. Okay, so I'm going to do my first asymptote at pi over 2, then 3 pi over 2. Okay, and then at your minimums and maximums, we're going to have your little bowls. So at 0, it's 1. Then at pi over 4, it's going to be your root 2. So you're going to have your half bowl right here. 3 pi over 4 is going to be at negative 1.4, then negative 1, then negative 1.4. So we're going to have a bowl facing, oh, well, that's terrible. Still terrible, but you know what? Close enough. Okay, and then up here, so at 7 pi over 4, it's going to be root 2. Then at 2 pi, it's going to be at 1. So we're going to have a half bowl about right here. Okay, so not as pretty as cosecant, but that's just because of the asymptotes. So really, what's going to happen is these are still going to continue. We're going to make these like full bowls. And then once again, because it's going to keep going, we're going to have all these bowls oscillating up and down throughout. All right. So for your domain in this case, now we just need to include, or not include, hello. We need to exclude the pi over 2's. So the pi over 2's here, so domain cannot equal pi over 2 plus pi k, where k is an element of the integers. Okay, then for your range, so same idea that we did for cosecant up here. So for cosecant, there we go. So we're going to go down indefinitely, and then we're going to go up indefinitely, but we still have this gap right here. Okay, so for the range, I'm going to go from negative infinity to negative 1, and then a union 1 to infinity. Oh my God. All right, so now for the number of cycles, I'm going to reference this back up here with cosecant. I think it'll be a little bit easier. So 1 negative and 1 positive bowl, which I should have talked about this up here, is going to equate to 1 complete cycle. So that's why over here, when we did the number of cycles, that's why we just did 1. I know there's 2 bowls, but 1 positive and 1 negative is going to account for all the values, which is why there's only 1 cycle. So over here, we have 1 complete negative bowl over here, and then we have 2 half positive bowls. So that's going to give you 1 complete cycle, which is going to give you a period of 2 pi, which gives you a frequency of 1 over 2 pi. Then your asymptote's going to be the same as your domain, but we are equal. So in this case, x equals pi over 2 plus pi k, where k is an element of the integers. And then zeros, well, we don't cross the x-axis, so none. Sorry, I'm going to try to speed this up because I'm starting to cough a lot more. Okay, now for cotangent. So cotangent is the same as 1 over tangent of x. Okay, so this one is really similar to tangent. I'll kind of give you a spoiler. It just kind of goes the other way. It's like a reflection over the x-axis almost. Almost. I'm going to re-emphasize almost. Shape-wise, yes, but the asymptotes are different. Okay. So in this case, what I want to re-emphasize with cotangent is cosine over sine. So what I want to focus on is I'm actually going to draw a sine to kind of give me an idea of where the asymptotes are. So sine is going to have this little pattern here. Oh, wow, terrible. Okay, so remember, every time the denominator function hits 0, that's where you're going to have your asymptotes. So what this tells me, I'm going to have asymptotes at 0. I missed. Go over there. At 0, then at pi, and then also at 2 pi. Ta-da! All right, so now I'm going to get rid of sine because that's really all I needed it for. Now it's just in the way. Okay, so now that we know where the asymptotes are, now I can actually go over here, fill out the table, and then wherever you see the asymptotes, that's where it's going to be undefined. All right, so this is the reciprocal of tangent. So you can take some time, you can find out what those values are going to be when you just do the reciprocal of your tangent values, but I'm going to kind of spoil it. So at 0, we're undefined. Pi over 4, we're 1, then 0, then negative 1, then undefined. Then 1, 0, negative 1, and undefined. Okay. So at pi over 4, I'm going to go ahead and start graphing these points. So we have 1, 0, negative 1, undefined. 1, 0, negative 1, undefined. So that's kind of your pattern. Okay, so when I draw my little graphs, so now we're actually going to start at the top left up here, and then work our way to the bottom right of each of these little sections. So they're going to decrease. And make sure you make them curved. Because once again, they have to, I missed. They have to be curved. Close enough. All right, and then just like before, we're still going to have a whole bunch more different cycles. So like over here, it's going to be indefinite. Like they're going to keep repeating throughout the entire function. But this is just what we see. Okay, so for your domain, so let's exclude our asymptotes, which means we're going to exclude the pi k's. So x cannot equal pi k, where k is an element of the integers. Okay, your range, it's going to go up and down indefinitely, so that's negative infinity to positive infinity. Number of cycles, well, we actually have 2. Okay, and then the period is pi. Remember, tangent and cotangent have periods of pi by default. All right, and then frequency is going to be 1 over the period, so 1 over pi. Asymptotes is going to be the same as your domains. So x equals pi k, where k is an element of your integers. And then your zeros, so it's going to be at the pi over 2's. So what that tells me is we're looking at pi over 2 plus pi k, where k is an element of the integers. All right, and then on this very last page, what's going to happen is now you're just evaluating. It's the same as what we did in the unit circle before, but the only difference is now you're also going to be evaluating your secant and cosecant values. So I'm going to go ahead and just kind of spoil it for you. So sine and cosecant trig ratios are going to be reciprocals. Cosine and secant trig ratio values are going to be reciprocals, and then tangent and cotangent trig values are going to be reciprocals. So, for example, these first 9 problems are copy and pasted for 10 through 18. The only thing I did is I just used the reciprocal ratio. Nope, I missed. So cosine of pi over 4 is now going to be secant of pi over 4. And then, for example, number 4, sine of 5 pi over 4 is now going to turn into cosecant of 5 pi over 4. So let's evaluate just a couple of these. So cosine of pi over 4, well, I know that's going to be root 2 over 2. So then if I were to come down here to number 10 and do secant of pi over 4, well, that's going to be 1 over cosine of pi over 4, which means I would do 1 over root 2 over 2. So when you divide by a fraction, that's the same as multiply by the reciprocal. So 1 times 2 over root 2, and then we got to rationalize. So when you rationalize, multiply across, so that's going to give you 2 root 2 over 2, which is just going to give you root 2. So that's where those values come from. So same idea with sine of 5 pi over 4. So sine of 5 pi over 4 is going to give you a negative root 2 over 2. But then if I go down to number 13 and I do cosecant of 5 pi over 4, well, cosecant is 1 over sine of 5 pi over 4, which means I want 1 over negative root 2 over 2. So, of course, when you simplify, that's going to be 1 times negative 2 over root 2. Once again, you're going to have to rationalize. So multiply by root 2 over 2, your funky form of 1. So when you multiply across, you're going to get negative 2 root 2 over 2, which is negative root 2. Okay, so same idea. Some of these are going to use coterminal angles. So like your cosecant of negative pi over 3, you have your coterminal angles. So some of these is going to be about working smart, not hard. So